Hello everyone. Today we are talking about non-convex low-rank modeling of tensors. So you can see there are three topics in this talk. That is low-rank modeling, non-convex, and tensors. Firstly, we introduce what is low-rank modeling. So please look at those pictures. As it is well known, so in MATLAB we store a picture or image as a matrix, and each element of a matrix corresponds to one pixel of the picture of the image. Now if we look at those images, for example, pay attention to this Chinese character. So you can see this Chinese character is very symmetric, and this human face is of course very symmetric. If we look at this picture, so you can see this picture in the math department. So in this picture, you can see this column is identical to this column and this column. So that means what? That means those images have a global symmetric structure. So if we store those images as matrices in MATLAB, so those matrices are always of low rank. Low rank means that the matrix has a rank much smaller than the number of columns. So this is called low rank property of the images. So in our research, it is very important. It is very useful to recover the low rank structure of an image. Why this is very important? For example, if we look at this image, so this is a corrupted image. For those corrupted image, so if we want to recover the low rank structure, that is the low rank background. So you may think about we can use PCA to find out the low rank structure, but if the image is very corrupted, if there are lots of missing values or some noise there, so it is impossible to use PCA to recover the low rank structure. And therefore, people introduced what we called robust PCA. Robust PCA is to not only recover the background of an image, the low rank background of the image, but also the sparse error. That is, we want to decompose a corrupted image into two parts. One part is low rank and one part is sparse. So this is called robust PCA. Robust PCA was introduced by Candice, Li, Ma, and White. So this method has been widely used in real-world application. For example, if we look at this video sequence, you know that for example, in the mall, so there are several cameras. So in the cameras, they recorded some image. For example, in this image, the camera recorded the background and the people moving around. So you know that the background cannot change, but different time, different people moving around. So the human cannot remain the same. So that means if we look at those three pictures, so those three pictures has the same background, which is low rank. For the people moving around, we can consider those people as sparse error. So we can recover the background of those images with the sparse error. So in practice, we can store those images in a matrix. For example, this image, we can stretch this image into a column of the matrix, a column of the matrix, a column of the matrix. So we have a big matrix of 200 columns. And then we can use robust PCA to recover the low rank background of those video data and plus a sparse error. So this is the application of robust PCA of a matrix data. Now if we look at those images, you know that for matrix data, so we can plot the columns in a high dimensional space. But you know that some columns are highly correlated. That means those data points concentrate in several subspaces. So you can see those data points concentrate in those three subspaces. Of course, there are some outliers, but that's like the sparse error before. Okay. So this is called subspace clustering. Subspace clustering is different from traditional clustering methods. That is, in subspace clustering, we try to use the geometry of those subspace, to cluster data into multiple subspaces. So this was proposed by Al-Hamifa and Vidal. So those are old low-rank modeling for matrices. Now we go to tensors. So why we need to study tensor? So for example, if we look at this grid level image, this human face, so we know that we can store this human face in MATLAB as a matrix. However, if we have such a video sequence, so it is not very natural to store those video sequence as a matrix, because if we do this, we will break the structure of those images, and we will lose some useful information. So that is, if the dataset has a dimension bigger than 3, so it is not sufficient to use the matrix representation. So we need to introduce a third-order tensor. So you can see, for example, here, a third-order tensor is composed by several slices of matrices. For example, if we look at this color image, we know that the color image for the color direction, there are 3 channels. That is red, green, and blue. So it is very natural to represent a color image as 3 slices of matrices, and each slice so those 3 slices of matrix construct a third-order tensor, and you can see in the third direction. So in third direction, there are 3 matrices. So the third direction has dimension 3. So that means we can consider a color image as a tensor. Also, if we look at this facial image data, so we can represent this facial image as a third-order tensor. One direction is the impressions, one direction is the different people, and one direction represents different views, and the fourth direction represents illuminations. So that is, we can construct a third-order tensor, a fourth-order tensor, to represent this facial image. So that is why we need to introduce a third-order tensor or even high-dimensional tensor to represent, a high-dimensional data. Now to study tensors, so we need to introduce some very useful mathematical tools. For example, when we do the dimension reduction of two-dimensional data, we need to use the SVD of a matrix, and we can throw away the components with smaller singular values. But for tensor, it is very useful to introduce the tensor SVD. The tensor SVD is to decompose a third-order tensor into three other tensors. The U and V are orthogonal tensors, and sigma is a diagonal tensor. So this kind of TSVD was introduced by Kummer and Martin. And this star here means they use some T-product. And T-product is a very useful algebraic operation. You can see the detail in this paper. And this is a picture for TSVD. That this kind of TSVD not only perform matrix SVD in the Fourier domain, but also you can see it can retain the Lorentz structure. So by using this TSVD, it is not hard to solve the tensor rank minimization problem. So this is the objective function. This means we want to approximate a third-order tensor X by using a low-rank tensor Z. And you can see here the original penalty is the rank of Z. The rank is a non-continuous function, so it is NP hard to compute. So we need to introduce some function, to approximate the rank of Z. The function can be convex or non-convex. So before, people used nuclear norm to approximate the rank of Z. So in our research, we try to use some non-convex rank approximation, like Chatain-P quasi-norm or log determinant. So why we need to introduce those kind of non-convex functions? The reason is that the nuclear norm is not always satisfactory. You know that the nuclear norm is the convex envelope of rank function. But if the singular value is very big, so there will be a big gap between the rank and the nuclear norm, because the rank is the number of the singular values, and the nuclear norm is the summation of singular values. So this was observed by Fazol, Hindi, and Boyd. So they introduced the log determinant to replace the convex nuclear norm. So here, there's a comparison of different rank approximation functions. You can see this is the nuclear norm. So here we consider only one element. So if this element is 0, that means the rank is 0. If the element is non-zero, that means the rank is 1. However, if this element is very big, you can see there's a big gap between the rank 1 and the nuclear norm. So we need to shrink less this element. If we use the log determinant or the Chatain-P norm, you can see the curve get close to this horizontal line. The curve. That means those non-convex functions can better approximate the rank. If the element is very big. So we try to use, non-convex regularizations. So now we consider this tensor rank approximation problem. And here we replace the rank of z by using log determinant. So by using the TSVD, this optimization problem can be solved very easily. That is, firstly, we transform x into the Fourier domain, and then we can form an equivalent rank minimization problem in the Fourier domain. And this problem can be solved very efficiently in Fourier domain. And then we can use inverse Fourier transform to get the corresponding elements in the original domain. And then by using the TSVD, we can construct the solution Z. So this is a standard procedure to solve the non-convex tensor minimization problem. Now, this kind of non-convex tensor minimization has lots of applications. For example, if we want to extend robust PCA from recovering a low-rank matrix to recovering a low-rank tensor. So this was firstly studied by Lu, Feng, Lin, and Yan, but they use the convex nuclear norm. But here we can also use Schatten-P norm to approximate the low-rank part of a tensor. That is, if we try to find the low-rank and sparse components of a third-order tensor, we can minimize this objective function. Because L has a low rank, so we try to use Schatten-P norm to approximate the rank of L, and to find the sparse component of a matrix X, we always need to minimize the L1 norm of a tensor of a tensor E. Okay. So this optimization problem can be solved by using ADMM algorithm. So because the Lagrange function is in this way, so we can use ADMM to solve this optimization problem very easily. So this is the iteration steps. So and you know that those steps has a very deep connection with neural network. Each iteration is like a layer in the neural network. So this method has a very deep connection with deep learning. This is our experiment. So if you look at this color image, we already tell you that color image is a third-order tensor, and the third direction has 3 dimensions. This is the corrupted image, and we can use TSVD to recover the low-rank part of the corrupted image in this way. So you can see this is very close to the original image. That means our experiment results are excellent. You can see here the number is very good. And we can also extend the subspace clustering into a tensor. That is, we can explore the multi-view data with n objects and v views. So we can form this multi-view data as a tensor. And D is the number of features, N is number of objects, V is number of views. And this kind of tensor multi-view clustering was proposed by Xie and Xie, Tao, Zhang, Liu, Zhang, and Qu. So in their work, they try to minimize the tensor multi-rank. In our research, we try to propose a log determinant representation of the tensor rank. So the method is to find out the self-expressive tensor Z. That is, x is approximately equal to x times Z. Here, this is the T product. And Z here is the self-expressive tensor with a low rank. Not only a low rank, but also has a block diagonal structure. So this is our optimization problem. You can see for each view, this is same to the matrix subspace clustering, but we store the image, those images in different view as a tensor, because in this way, we can directly capture the high order correlations among all the different views. So this method is very efficient. In our experiments, we work on those data sets, and you can see the results are better than old methods. It's much better than using the classical method. By using it is much better than the classical method using matrix methods, and it is also much better than the multi-view clustering method using the nuclear norm. In the future, we try to do more and more applications involving tensorial data. For example, the background and foreground separation in video. And we will study more and more applications of non-convex formulation.